After doing Boyle's law, here's one more uh, basic fundamental gas laws and the Charles law. Right? And again, this is also something which you would have studied in the lower classes. So I'll start with the statement. What Charles law says is that for a gas at constant pressure, right? If you have a gas system and if you maintain the pressure constant, then the volume of the gas is directly proportional to the temperature. Right? So if I take a system of gas, let's say this, again the very common piston cylinder arrangement gas, and if I maintain constant pressure and if I increase the temperature, for example if I heat it up, and this gas system will expand, the volume will increase, the piston may go up because of the heat generated over here and the energy given to the molecules. And what we see is that the increase in volume is proportional to the increase in temperature, and therefore we say volume is proportional to temperature. So this is a very basic simple concept of Charles law, and we'll study it more detail now. Let us say if we have a gas at 0 degrees Celsius, right? And let us say the volume at 0 degrees Celsius is V0, and now we heat it up to say T1 degrees Celsius and the volume becomes V1, and also let us say temperature T2 degrees Celsius, the volume is V2. So if I plot a graph of P versus V, let us say I plot a graph of volume, let us say in meter cube, and here temperature in degrees Celsius, right? So this would be 0 degrees Celsius. Let us say this is temperature T1, this is temperature, let us say T2, right? Now since volume is proportional to temperature, right, the graph would be a straight line going up because they're directly proportional relationship. So you'll get a graph something like this, going up something like this. So this is 0 degrees Celsius, T1 degrees Celsius, of course, T2 degrees Celsius up. And here the volume at 0 degrees Celsius, this is V0, and this volume would be V1, this volume would be V2, and we'll get a graph like this. Now here I'll introduce another concept to this. Let us say that we extend this graph in the negative side of temperature. Let us say I extend this, right? This graph. This graph will cut the x-axis or the temperature axis at some particular point over here. And it turns out that this temperature at which this graph cuts it is minus 273.15 degrees Celsius. And this temperature, minus 273.15 degrees Celsius, is known, as you know, as absolute zero. Right? Again, absolute zero is the temperature at which we have no molecular motion. So, no molecular motion and no energy, right? The temperature is so low that at that temperature these gas molecules, they lose all their energy, there's no molecular motion. But this, to attain this state is not possible. You know, a gas cannot reach this state. It cannot reach a temperature of minus 273.15 degrees Celsius because the volume of the gas at that point, this is the volume scale, the volume becomes zero, right? The volume is zero. Now a gas cannot have zero volume, right? What actually happens, or what really happens, is before the gas achieves this minus 273.15 degrees Celsius, at some temperature over here, it liquefies, right? So this is a theoretical construct, a very important construct, but a theoretical construct, not possible in real life. So this temperature is known as absolute zero, and in 1848, Lord Kelvin devised a scale, right, based on this, and which is known as the absolute thermodynamic scale or absolute zero scale. And this particular point was known as, or was identified as 0 Kelvin. So this is 0 Kelvin. This is 0 Kelvin. And this is minus 273.5 degrees, 15 degrees Celsius, and on Kelvin scale it is 0 Kelvin. So this becomes 273 Kelvin. You add 273 over here. If I add 273 to minus 273, I get 0 Kelvin. Similarly, I would add 273, so this point is 273 Kelvin on the Kelvin scale. This would be T1 plus 273, this would be T2 plus 273. And this Kelvin, this will be Kelvin, And T1 plus 273 Kelvin will denote by T1, capital T1 Kelvin, capital T2 Kelvin. So when we use small T1 and T2, that is degree Celsius, and capital T1 is temperature in Kelvin. Okay, coming back over here. So if you look at the Kelvin scale, we have got all the temperatures in Kelvin scale also over here. So I can write here temperature in Kelvin. Okay. Now, if I look at this particular triangle, right? Let me now change the color and show the triangles that I'm looking at. If let us say we focus our attention on these triangles, right? Let us call them O, A, B, C, D, and E, F. Right? If I focus my attention on these triangles, and let us say first I focus on triangle OCD, right? This particular triangle. Then, if I take change in volume, right? V1 minus V0, right? That is V1 minus V0. This is V0. V1 minus V0 upon V0 minus 0 upon V0 minus 0. So I am subtracting the volumes. V1 minus V0 upon V0 minus 0. Right? This is the Kelvin. So V1 minus V0 and V0 minus 0, because the volume over here is 0. That will be equal to, if I look at temperature, here I have V1 minus V0. So if you look at the corresponding temperatures, I will have T1 minus 0. So T1 minus 0. And for V0 minus 0, the corresponding temperature will be 0 minus 273. Right? I hope you got this. Let me once again repeat this. V1 minus V0. So V1 minus V0 upon V0 minus 0 is equal to T1 minus 0 upon 0 minus 273. Right? And if I simplify that, I'll get V1 minus V0 is equal to, this is V0, so I can take V0 over here. This is T1 and this will be 273. So I can write this as V1 is equal to V0 plus V0 T1 upon 273, and therefore V1 is equal to V0 into 273 plus T1 upon 273. Okay, this is for triangle OCD. Right? And I can do the same for triangle OEF. OEF. In the first case, I did between V1, 0, V0 and 0. Now I'll do between V2, V0 and 0. So if I do the same calculation, a similar calculation, right, I'll get V2 minus V0 upon V0 minus 0 is equal to T2 minus 0 upon 0 minus 273. And if I simplify it exactly in the same way that I have done over here, I'll get V2 is equal to V0 into 273 plus T2 upon 273. Right? Now, if I take the ratio of these two, say for example, I take V1 upon V2, right? Then I'll get V0 into 273 plus T1 upon 273 divided by V0 into 273 plus T2 upon 273. And doing a little bit of math over here, V0 cancel, 273 cancels, so I'll get 273 plus T1 upon 273 plus T2, V1 upon V2. And what is 273 plus T1? 273 plus T1 is T1, temperature T1 in terms of Kelvin. This T1 is in degrees Celsius. If I convert it into Kelvin scale, this will be T1 upon T2. And therefore, V1 upon V2 is equal to T1 upon T2. This is also the statement of Charles' law in terms of absolute temperature. So, whenever we're looking at Charles' law here on, remember V1 upon V2 is T1 upon T2, or V1 is directly proportional to T. You may also write this as V1 is proportional to T, where T is the temperature in Kelvin scale. So this is the background or the understanding of Charles' law. Charles' law also helps us understand absolute zero by doing some extrapolation work. In the next video, we will look at the third basic law of gases, which is the law of pressure, and we will do an exactly similar exercise. The only difference being the graph, instead of being V versus T, would be P versus T. Right? See you in the next video. Thank you.